Imagine a world with an ocean so vast it could have covered the entire planet. Now imagine that ocean just vanishing. Well, that's not some sci-fi plot. That's the very real story of Mars. Today, we're going to investigate one of the greatest disappearing acts in the entire solar system. Where did an entire planet's worth of water actually go? I mean, this is the question, right? This is what has kept planetary scientists completely obsessed for decades. We're not looking for some lost river or a little dried-up lake. We are searching for an entire ocean. So how on earth do you even begin to solve a mystery on that kind of scale? You just have to look at this comparison to see how dramatic the change was. On the left, you've got ancient Mars, a vibrant blue world that, might have looked a lot like a young Earth. And then on the right, the Mars we see today, a cold, red, frozen desert. The biggest mission in Mars exploration has always been to figure out what happened in between. Okay, so to even have a prayer of solving this mystery, we first need to get a handle on just how much water we're actually looking for. And it turns out the clues are literally carved into the face of the planet itself. When you look down from orbit, you can see these incredible scars of ancient rivers etched all over the Martian surface. And we're not talking about small streams here. We've mapped these huge drainage basins, some of them rivaling the size of the Congo River Basin on Earth. This is pretty much ironclad evidence that Mars once had a powerful, long-lasting water cycle, complete with rain and enormous flowing rivers. So how do we know these rivers were around for a long time and not just some flash flood? Well, this is where planetary geologists really get to act like detectives. And the prime scene, the Martian surface, is absolutely full of clues. Okay, so one of the weirdest and coolest features on Mars are these winding ridges that just snake across the landscape. As you can see here, they're actually what we call inverted channels. So picture a river flowing for thousands of years. Its bed gets all compacted and hard. Then, over billions of years, the wind just scours away the softer plains all around it, leaving the old, hard riverbed standing out. The fact that these rivers meandered, creating those lazy curves, is the smoking gun. It proves the water was flowing gently and consistently for a very, very long time. And don't just take my word for it. As planetary scientist Dr. Michael Mallon puts it, this evidence is unequivocal. The geology is practically screaming at us that Mars wasn't just briefly wet. It had stable, persistent rivers for maybe millions of years. And of course, wherever you find long-lived water, you have to ask the question of life. The Perseverance Rover recently spotted these leopard spots on some rocks in an ancient lake bed. Now, it's not definitive proof, not at all, but these textures look strikingly similar to patterns created by microbial mats on Earth. It's what scientists call a potential biosignature, a tantalizing clue that this ancient water might have actually been a habitat. For years, this story kind of ended there, a watery past, a dry present, and a big mystery. But the biggest clue to solving where all that water went didn't come from a camera looking at the surface. It came from an instrument that was listening to the very heartbeat of the planet. Yeah, the big breakthrough didn't come from a rover that was looking for water at all. It came from NASA's InSight lander, a robotic geologist designed to do one thing, just sit perfectly still and listen for Marsquakes. And in doing so, it gave us the first ever CAT scan of the planet's deep interior. What it found was absolutely astonishing. So as InSight listened to seismic waves from things like meteorite impacts ringing through the planet, it noticed something really strange. About 5 to 8 kilometers down, those waves suddenly slowed way down. Now, seismic waves travel fastest through solid, dense rock. So a slowdown like this, a low-velocity zone, it means they're moving through something much less dense, something fundamentally different. So what could possibly be causing this slowdown? Well, the data pointed to only one real conclusion. The rock in this zone wasn't solid. It was heavily fractured with a porosity of 20 to 30%. I want you to try and imagine a planet-spanning layer of shattered rock, like a giant subterranean sponge. But a sponge can be wet or it can be dry. The final piece of this puzzle was the temperature. Calculations based on the planet's own geothermal heat show that at this depth, the temperature is between 10 and 30 degrees Celsius. That is well above freezing. It's a shockingly comfortable sweet spot. So, when you put all of these clues together, the slow seismic waves, the porous, spongy rock, and the warm temperatures, it leads to one breathtaking conclusion. This zone is a massive, global aquifer filled with liquid water. The mystery is solved. Mars didn't lose its ocean to space, it drank it. The water is still there, locked away deep underground. This discovery, it changes everything. I mean, it means there's a warm, wet environment on Mars that has been stable for billions of years. So the next question is pretty much unavoidable. Could something be living down there? And how would life even survive in total darkness, miles beneath the surface? Well, the answer isn't sunlight, it's the rock itself. There's this incredible process called radiology that can basically turn a planet's crust into a giant geological battery, creating a steady supply of energy that life could actually use. So here's how that geological battery works. First, you have radioactive elements that are just naturally in Martian rock, and they decay. That radiation zaps the water molecules all around them, splitting them apart. This whole process releases hydrogen gas, which is a really potent chemical fuel. So subterranean microbes could literally eat that hydrogen to get energy, completely independent of sunlight. It's a totally self-contained ecosystem, powered by nothing but rock. Okay, so we can't drill 5 kilometers down into Mars. At least not yet. So how do we even begin to hunt for this potential life? We look for its breath. We start searching for any waste gases that might be produced by this deep biosphere and are maybe seeping up to the surface. And that leads us to one of the most maddening puzzles on Mars, the methane enigma. As you can see here, our rover on the ground, Curiosity, frequently detects these little puffs of methane gas. But then our satellite in orbit, the Trace Gas Orbiter, looks down at the whole atmosphere and sees basically nothing. How can both of these things be right? The best explanation we have for this contradiction is that methane is probably bubbling up from very specific localized vents on the surface. And then it's getting rapidly destroyed by solar radiation in the thin atmosphere. This would mean it doesn't have time to build up to a level the orbiter can see from above. And it's a huge clue that something, either geology or biology, is actively producing gas beneath the Martian surface right now, today. Which leaves us with this final, really profound thought. The search for water on Mars has led us, against all odds, to a hidden ocean. And the search for life has led us to these mysterious plumes of methane. So the question we absolutely have to ask now is this. Are we finally detecting the faint, intermittent breath of a living world, hidden just beneath our feet?